Hello everyone, welcome back to Native Engineering. Today we are going to do an exercise on stress and strain. But before we get to the exercise, I want us to discuss the graph that is on your screen right now. This is called a stress and strain graph. This side we are having the force or the stress, and this side we are having the extension or the strain. So let's say we are having a spring. What happens to a spring when we apply a force? Obviously, the spring will increase in length. And after we remove that force, as soon as that force is being removed, the spring will go back to its original shape. We call that property elasticity. Elasticity is the property of a material to return back to its original shape after the force that was causing its elongation or compression has been removed. So from 0 to A, there is a force that is applied to the spring. The force is increasing, and as a result, you can see that the extension is increasing, meaning the spring is increasing in length. From A to B, I mean from 0 to A, the object is respecting what we call Hooke's law. Hooke's law states that the extension is directly proportional to the force or to the load that is causing it. As you can see, we are having a straight line from 0 to A. Point number A is called the limit of proportionality, meaning that if we get to point number A and still apply force, beyond number A, the object is no longer respecting Hooke's law, meaning the force and the force increase and the extension are no longer proportional. And then we have number B. Number B is elastic limit, meaning beyond number B, even if the force is now removed, the spring will no longer go back to its original shape or size, or length for that matter. And then we have number C. Number C is called the yield point. And then we have number D, where we are going to have the ultimate stress or maximum stress. This is the largest force that can be applied to this material. And then we have point number E. Number E is the fracture point. This is where the object will tear apart because as a result of the force that is being applied to that material or to the spring that we are dealing with. So yeah, this graph, it's important that you know it. Then we have something else that we call the factor of safety. Factor of safety. Factor of safety, it's given by the ultimate stress divided by the working stress. The ultimate stress will occur here, and the working stress it's the safe stress to apply to that object. It's within the Hooke's law. The ultimate stress, it's within this. The working stress rather, it's within the Hooke's law. And then the ultimate stress is the maximum force that can be applied to that material. So from here, we are going to look at our question. And this is the exercise that we are going to do. They say figure 1.10 shows a round steel rod subjected to a tensile load of 50 kilonewton. Young's modulus is 200 gigapascal. And then the questions, they say calculate, number 1, the maximum stress in the rod, calculate the minimum stress in the rod, and then number 3, they say total strain in the rod. Number 4, they say total change in length. This is the information that we are given. We're given this member and the force that it's applied, the tensile force that is applied is 50 kilonewtons. We're given the length of this. We're going to name it member number 1. Because they have two different cross-sectional areas, we're going to divide them into 2 and treat them separately as 2 objects. So we have this one, we're going to name it number 1, and we have this one, we're going to name it number 2. The length of number 1 is 80, the length of number 2 is 100. The force, it's the same, and we are given the modulus, the Young's modulus as 200 gigapascal. And then question number 1, they say calculate the maximum stress in the rod. We know stress is given by force divided by area. Now the question is, which one of these two is going to experience the maximum stress since we are having the same force? So looking at the two members, for member number 1, we are only dealing with this area because this is a hole. So if we were to look for the side view, it will be something like this. This is the only area, only part that we're dealing with, since this is a hole. So looking at our formula and remembering what stress is, we know that the smaller the area, the larger the stress will be. So in this case, we're having an object. This has a smaller area compared, object 1 has a smaller area compared to object 2, because when we're dealing with object 2, we're dealing with the whole circular part. There is no hole, but for object number 1, there is a hole, meaning the area here is less than the area in object number 2, meaning the maximum stress will occur in object number 1. Therefore, we're going to say the force 50 times 10 to the power 3 divided by the area, which will be 0.06 squared minus 0.054 squared. We are calculating for the area of this circle and minusing the whole. And then I got that our answer here is equals to 31.831 megapascal. If you are not sure which one will give you the maximum stress, which one will give you the minimum stress, calculate for the stress for this member and for this member, and then see which one is the largest. And then we go to number 2. I'm going to erase all of this. Hopefully you have the diagram. They say calculate for the minimum stress. The minimum stress will occur on member number 2, and stress is given by force divided by area, which will be, the force is 50 times 10 to the power 3 divided by the area, 0.06 squared, which will give us our stress is 17.684 megapascal. This is the minimum stress. And if you compare the numbers, you can tell that this is smaller than the stress that we calculated in question number 1. This is 1.2. In 1.1, it was 31.831. Now we're having 17.684. This is the minimum stress. The one that we calculated in 1.1 was the maximum stress. And then we go to question number 1.3. They say calculate the total strain in the rod. We know strain, it's given by change in length per unit length. But in this case, we do not have the change in length. So we are going to use another formula, which is Young's modulus is equals to the stress divided by the strain. Since we were given the Young's modulus as 200 gigapascal, we are going to use this formula to get strain number 1 and strain number 2, because we are asked for the total strain. We know strain number 1 plus strain number 2 will give us the total strain. So we're going to start with strain number 1. Strain, we make it a subject of the formula, will be stress divided by the Young's modulus. For number 1, strain number 1, we are going to use stress number 1, which is the maximum stress. And the maximum stress we calculated and got that it is 31.831 times 10 to the power 6 divided by Young's modulus, which we are given is 200 times 10 to the power 9. And this gave me a strain of 1.592 times 10 to the power negative 4. And then we calculate for strain number 2. Strain number 2 is equals to stress, which will be the minimum stress, divided by Young's modulus, and this will be 17.684 times 10 to the power 6 divided by 200 times 10 to the power 9, and this gave me a strain of 8.84 2 times 10 to the power negative 5. And then we are going to calculate for the total strain using these two values, and we know the formula to calculate total strain is equals to strain number 1 plus strain number 2, which will be our strain number 1, we got it as 1.592 times 10 to the power negative 4 plus strain number 2, which is 8.842 times 10 to the power negative 5, and then we get our total strain as 2.476 times 10 to the power negative 4. This is our total strain. And then we go to the last question. They say calculate the total change in length. The total change in length is given by change in length number 1 plus change in length number 2. So for change in length, we are going to use the formula for strain. We know it's given by change in length divided by the total length. So we're going to start with change in length number 1. We make it the subject of the formula from here. We're going to have strain 1 times change in length times the original length number 1. And then our strain number 1, we got it as 1.592 times 10 to the power negative 4 times our length, which will be 0.08. This one we are given. And then I calculated here and got my answer as 1.274 times 10 to the power negative 5. This is in meters. And then we go to calculate for change in length number 2. It's 8.845 times 10 to the power negative 5 times 0.1, and I got our answer as 8.845 times 10 to the power negative 6. This is also in meters. And then from here, we're going to come to this formula and say change in length number 1 plus change in length number 2. Change in length number 1 is 1.274 times 10 to the power negative 5 plus 8.845 times 10 to the power negative 6, which will give us 2.159 times 10 to the power negative 5. Or you can, this is in meters, you can just write it, convert it to millimeters and write it and get 0.0215 millimeters. Whether you leave it here or you leave it here, it's your choice, unless you are told to calculate and leave the final answer in millimeters. You can also leave it here if you are not told. And that's it for this video. I will see you on the next one.